Welcome to the Deep Dive, the place where we dig into dense research papers so you don't have to. We pull out the core ideas to help you stay ahead.
Yeah, cutting through the noise.
Exactly. And today, we're tackling a really provocative new scientific survey. It's aimed squarely at the whole artificial general intelligence debate.
Right, the one with the very memorable original title.
Yes, that one. But we're focusing on the serious framework inside. Think of this as our way to get a handle on the structure of AGI research as it stands right now.
And our mission here is pretty clear, especially for you, our technical audience. We want to get past the usual media hype, define AGI scientifically, by function. Then we need to dissect the main tools being used, basically search and approximation. And finally, look at the guiding philosophies, the sort of meta approaches dictating what we're actually optimizing for.
Okay, sounds good. Let's jump right in. For anyone listening on the go, maybe driving, running, here's the 60-second version, the absolute core takeaways from this paper. Key insight 1, defining AGI. Forget human level for a moment. The paper argues for a functional definition. AGI as an artificial scientist.
Right. It's about being a goal-seeking system, but crucially with limited resources.
So it needs autonomy, planning, learning cause and effect, and balancing, exploring for knowledge versus acting for profit or achieving goals.
Precisely. Key insight 2, the tools. AGI work really rests on two pillars. There's traditional search think symbolic reasoning, A.
The classic stuff.
Yeah, and then modern approximation neural networks, large models, that whole world. The big breakthroughs lately, AlphaGo, OpenAI's reasoning models, they're hybrids.
Fusing both.
Exactly, fusing both to get around the limits of each one. Search gives precision, approximation gives scale.
Got it. And key insight 3, the meta approaches, or the Maxing principles. What guides the development?
3 main philosophies. First, scale maxing. Just throw more resources at it. Compute, data, parameters. That's the current dominant trend, what the paper calls the Embiggining.
We've all seen that.
Then there's Simp Maxing. Maximize simplicity like compression. Think Kolmogorov complexity.
Occam's razor, basically.
Sort of, yeah. And finally, W maxing. This one's a bit different. Maximize the weakness of constraints on function. Focus on the whole system's adaptability.
Okay, weakness constraints. We'll need to unpack that.
We will. But the conclusion, long story short, the Embiggining, while powerful, is hitting serious walls. Sample efficiency, energy costs.
Right.
So the path forward for a truly general AGI, one that's sustainable, needs a smart fusion of tools, guided more by Simp Maxing and especially W Maxing's principles.
Okay, that's a fantastic overview. Let's dig into that definition problem first. You mentioned moving past hype. Melanie Mitchell famously called AGI a Rorschach test.
Yeah, everyone sees what they want to see.
So the paper pushes back hard against defining AGI as human-level intelligence. Why is that such a problem? Why ditch the anthropocentric view?
Well, it's a major anthropocentric pitfall. If you aim for human level, you risk just building in all our human biases and inefficiencies.
Right, you're mimicking the flaws too.
Exactly. We don't necessarily want a perfect human mimic. We want something maximally effective. Plus, human level is just. It's incredibly hard to quantify scientifically. Is it passing a Turing test?
Which might just mean you built a convincing chatbot.
Precisely. Not necessarily general intelligence.
So before this artificial scientist idea, what were the main theoretical definitions people were using? I know there was a lot around generalization, compression.
Yeah, that's the Leghorn intelligence idea, drawing heavily on Kolmogorov complexity. It basically connects intelligence to Occam's razor. The simplest explanation, the shortest program that captures the data, is the most general, the most intelligent.
It sounds elegant mathematically. But the paper argues this falls apart because of something called computational dualism. What on earth is that?
Okay, so computational dualism is this idea that you're treating the AI's mind, the software, as totally separate from its body, the hardware and its environment, the context it operates in.
Ah, okay.
Think about how we actually measure success. It's not just the software, right?
Yeah.
It's $3 ones, F2, V3, so $30 F2 ones are the agent software, 2 is the hardware it runs on, and 3D32 is the environment or the evaluator judging it.
So trying to judge intelligence based only on the software F$ complexity, that's the dualism.
That's the trap, because the performance depends entirely on the whole chain. You could have brilliant software that runs terribly on the wrong hardware or produces results nobody cares about in that environment.
It's like judging a recipe without considering the oven or the ingredients.
Exactly. And the choice of your theoretical interpreter, your ideal universal Turing machine, can actually make any program seem optimal or simple. So judging $1 in isolation becomes well, kind of meaningless, or at least subjective.
Okay, I think I get it. The pure code complexity isn't enough. We need a definition that embraces the whole system hardware, software, environment. So, what's the paper's answer?
They land on Wang's definition. Intelligence is adaptation with limited resources.
Adaptation with limits.
Yes. That limited resources part is key. It forces you to consider the whole system, the context, the constraints. It avoids the dualism trap. And that leads directly to their functional definition. AGI is an artificial scientist.
Because the scientist has to adapt, work with limits.
Precisely. They need autonomy, they need to plan, learn, cause and effect, and constantly make that trade-off. Do I explore more to learn? Or do I exploit what I know to achieve a goal? It captures the dynamic nature of real intelligence.
That makes a lot of sense. An artificial scientist needs to be incredibly versatile, which brings us to the tools. Sutton's bitter lesson, the idea that general methods that scale always win in the long run, does that still apply here?
It does, broadly speaking, but we need to be careful about what general and scale mean in practice. The paper identifies the two fundamental toolkits, search and approximation.
Search first, symbolic AI, right? Like Deep Blue playing chess.
Yep, that's the classic example. Search works by exploring a defined structure, a game tree, a logical space. Think A for pathfinding or theorem provers.
And the big advantage is?
Precision and interpretability. Search can give you provably correct answers, and you can usually understand why it reached that answer. It's fantastic for structured planning.
But it hit limits, didn't it? Why isn't it dominating everything now?
Efficiency is the killer. Searching huge state spaces just explodes combinatorially. It gets incredibly expensive computationally.
Okay.
And maybe more importantly for today, traditional search is often sequential. It doesn't map well onto modern hardware like GPUs, which are built for massive parallel processing, originally for graphics.
Right, matrix multiplication monsters.
Yeah, exactly. So search tends to be practical only at higher levels of abstraction where the space is smaller.
Okay, so search is precise but slow and doesn't fit the hardware well. That leads us to the current champion. Approximation. Modern ML.
Right. CNNs, transformers, all that. Approximation is basically statistical pattern matching. You take a model, you tune its parameters based on vast amounts of training data.
And its strengths are obvious.
Absolutely. It handles noisy, high-dimensional data incredibly well, and crucially, it's massively parallelizable. It loves GPUs, that's why it scales so effectively right now.
So if it scales so well, what's the problem? The paper sounds worried.
The core issue is that it's inherently an approximation. It's statistical, not precise. It can be unreliable, hard to interpret. But the really deep flaw, the one the paper hammers home, is its extreme sample and energy inefficiency.
Meaning it needs tons of data and power.
Astronomical amounts. It takes massive data sets and huge compute budgets to learn things that, humans might grasp much faster. And this inefficiency directly leads to brittleness. If you need millions of examples to learn something, you're going to be terrible at dealing with genuine novelty things you've only seen once or twice, the edge cases. An artificial scientist, by definition, has to handle novelty. Approximation methods, at least in their current scaled-up form, struggle badly with that.
Okay, so search is too slow. Approximation is inefficient with novelty. The logical next step seems to be combining them.
Bingo. That's where hybrids come in. Fuse the strengths of both to mitigate the weaknesses.
And the classic example is AlphaGo.
AlphaGo is the poster child. It used search, specifically Monte Carlo tree search, to explore possible game sequences, but it guided that search using approximation deep neural networks to predict move quality and win probability.
So precision planning guided by scalable pattern recognition.
Exactly. Best of both worlds. And we're seeing this pattern everywhere now.
Like with language models trying to reason, or solving the symbol grounding problem.
Absolutely. Neurosymbolic hybrids are a big area. You use neural nets approximation to take messy, real-world input, like images or text, and translate it into clean symbolic representations.
Grounding the symbols in perception.
Right. Then you can use search or logical inference, the precise tools to reason over those grounded symbols. Think about chain-of-thought reasoning in LLMs that's blending statistical generation with more structured processes. DeepMind's alpha geometry is another perfect example, combining neural guidance with symbolic geometry deduction.
So these hybrid systems are becoming more common. The paper also mentions larger frameworks, cognitive architectures that try to put all the pieces together.
Yeah, these are ambitious attempts to build more integrated general systems. They often involve modules for perception, memory, reasoning, action.
Like what? Any examples stand out?
Well, there's Hyperon, which is designed to be modular and distributed, integrating things like probabilistic logic networks with neural nets. It's aiming for something called discrete active inference. Then you have AER, which is fascinating because it focuses on self-programming and reflection. It's trying to build systems that understand causality, use analogy, and can actually adapt their own structure over time.
An AI that rewrites itself.
Kind of, yeah. And then there's NARS, the non-axiomatic reasoning system. Its whole philosophy is built around operating with AIKR, the assumption of insufficient knowledge and resources.
Always assuming it doesn't know everything and doesn't have infinite time.
Right, so it uses a very fluid, evidence-based logic system. It doesn't deal in absolute truths, but constantly revises its beliefs based on new information, all under resource constraints. It's designed for uncertainty.
Okay, so the takeaway is, hybrids and these complex architectures offer a path towards more general, robust AI, but maybe they risk becoming kind of ad hoc collections of tricks without a solid guiding principle.
That's the danger. Which brings us neatly to the final piece, the meta approaches. These are the underlying philosophies, the guiding principles for how we optimize development.
The maxing principles you mentioned earlier.
Exactly. 3 big ones. First up is scale maxing.
The embiggining.
The embiggining.
Yeah.
This is basically Sutton's bitter lesson put into practice. Maximize resources, compute power, data set size, model parameters, just make everything bigger.
And you can't argue with the results, at least initially. GPT-3, AlphaFold 2, these were huge leaps driven by scale.
Undeniably huge.
Yeah.
Throwing data centers at the problem worked for a while, but the paper argues it's hitting diminishing returns hard.
How so?
2 main things. First, the cost benefit is getting worse. You need exponentially more resources now for smaller and smaller gains in performance. It's becoming economically and environmentally unsustainable.
Okay.
And second, that fundamental flaw we discussed, extreme sample inefficiency. Scale maxing inherently optimizes for systems that need tons of data, which makes them fundamentally bad at dealing with true novelty, with the rare but important events.
So scale maxing is powerful, but maybe a dead end, or at least reaching its limits. What's the alternative? You mentioned simp maxing.
Right. Simp maxing is about maximizing simplicity. Think Occam's razor applied to AI.
Shorter code, simpler model, more general intelligence.
That's the idea. It underlies things like regularization and machine learning, the minimum description length, MDL, principle. And it reaches its theoretical peak in concepts like AI-XI or Leg-Hutter intelligence, which are based on Kolmogorov complexity, finding the shortest possible program to explain the data.
But wait, didn't we just critique that using computational dualism?
Exactly. The critique applies here too. If simplicity or complexity is just a property of the description language you choose, the specific Turing machine you're using, then is it really an objective measure of the underlying intelligence or the world?
It depends on the interpreter again.
Right. Simplicity is in the eye of the computational beholder. It's elegant theoretically, but maybe not the whole story for building robust embodied agents.
Which leads us to the third one, the one that sounded tricky, W-maxing. Maximizing the weakness of constraints on functionality. What does that actually mean in practice?
Yeah, it sounds counterintuitive, doesn't it? Maximize weakness. But think of it like this. Simp maxing tries to find the shortest, most elegant recipe. W-maxing tries to build the most robust, adaptable cooking machine, one that works well regardless of whether you give it a gas stove, a microwave, or a campfire.
Ah, okay. So it's not about the elegance of the internal code as much as the system's overall ability to function effectively across many different situations. F22, Fafrio 3 hours, maximizing non-specificity.
Precisely. It frames intelligence within the whole system, the agent and its environment. It's linked to ideas like inactive cognition. By weakening the collective constraints on how the system must function, you force it to become more generally adaptable and resilient. You're optimizing the entire agent environment loop.
And this isn't just theory. The paper mentions significant performance gains.
Huge gains. Experiments cited show W-maxing approaches yielded something like 110% to 500% better generalization than comparable simp maxing methods alone.
Wow, that's substantial. How does it achieve that?
The key idea seems to be delegating control to lower levels of abstraction. Think about biology. Control isn't just in the brain, it's distributed down to cells, to molecular machinery.
Making the whole system more efficient and adaptable locally.
Exactly. W-maxing encourages finding the most efficient implementation at every level, tailoring the system to its physical reality. This naturally optimizes for both sample efficiency, because it adapts better to sparse data, and energy efficiency, because it finds physically optimal solutions.
So let's bring it all together. We started with the Embiggining, this massive scaling effort.
Which gave us impressive results, but is hitting efficiency walls.
Right. So the paper argues the future isn't just more scale.
No. The future for creating that versatile artificial scientist, AGI, requires a more principled approach. It needs a fusion of tools, these hybrids, combining search and approximation, but guided by better principles. Less brute force scale maxing, more theoretically grounded simp maxing, and especially more system-level optimization through W-maxing.
Optimizing the whole stack, maybe even down to the hardware.
Potentially, yes. Optimizing the entire system for functional adaptability and efficiency.
Okay, so if W-maxing and efficiency mean potentially optimizing the physical form, mimicking biology's distributed control, that leads to a pretty wild thought to leave our listeners with.
Go for it.
If achieving true general intelligence efficiently means the system might need to search the space of possible physical embodiments, how long until we see AI moving beyond just software and actually starting to design or even become its own bespoke hardware? Thinking about things like self-organizing materials, soft robotics driven by the AI itself.
When the artificial scientist starts running experiments on its own body to improve its adaptation, that's when things get really interesting. A true fusion of mind and matter.
A fascinating, maybe slightly unnerving place to end. Thank you for unpacking all that.
My pleasure. Lots to think about.
Absolutely. Thanks everyone for joining us on the deep dive. We'll catch you next time.